Hey guys, welcome to today's class. Have fun.
Okay, today we'll be looking at the topic chemical combinations. Now, the tendency of the other elements to try to attain the stable duplet or octet state structure possessed by the rare gases is achieved during chemical combination. And by chemical combination, we are trying to say each element now in the periodic table are trying to attain a stable octet structure. Now, what do you mean by an octet structure? An octet structure is the configuration of electrons in the atom in orbitals which have the maximum number of electrons to occupy that shell. Now, for the K shell, the maximum number of electrons you can have is 2. For the L shell, the maximum number of electrons you can have is 8. For the M shell, the maximum is 18. Now, for an element to attain a stable octet structure, it has to have this complete number of electrons. A simple example is an atom of helium. Now, helium has 2 electrons in its outermost shell. It has an atomic number of 2. So by this configuration now, it is occupying the K shell and it has the maximum number of electrons 2. But in case of hydrogen, hydrogen has 1 electron, which is just 1. Now it is 1 electron short of the octet structure, or duplets in the sense 2, octets for 8. So in this case now, hydrogen will need 1 more electron to attain a stable state. So this process in which the atom of an element acquires electrons in order to attain this octet or duplet structure is what we refer to as chemical combinations. So of all elements in the periodic table, it is only the rare gases that have a complete octet state, which is group 0. That is why they are referred to as group 0. Group 0 in the sense that they don't need any electron further. They have a complete octet state. So the number of electrons in their orbits are usually complete. 2 for the K shell, 8, 18, and so on and so forth as you move into higher orbital levels. Now we have various types of chemical combinations which can occur between elements in the periodic table. Now the first common chemical combination we have is electrovalent or ionic combination. Now electrovalent or ionic combination. Now in electrovalent combination, there is a transfer of electrons from one atom to another atom. Now the transfer of electrons is from an atom which is usually metallic to another atom which is most times non-metallic. Now in electrovalent ionic combination, you have an electron donor, you have an electron acceptor. Now this is the valence electrons which is being transferred. Now on losing electron, okay, you have A and you have B. Now let's take for example an element. Okay, before we take an example, let's just look at the explanation. So you have a donor giving out valence electrons to an acceptor. Now on losing electrons, you have cations. Why? When you gain electrons, you have anions. The simple analogy, you have an element A. Now if element A has 12 number of electrons and it loses 2 electrons, of course it will become a cation. To become a cation, A2 plus, so a donor is a cation. Now it gives 2 to element B. Element B has 13 electrons. On gaining 2 more electrons, it becomes 2 minus. So this is what simply happens in electrovalent combination. And an atom of an element transfers its electron to another atom of another element so that it can obtain the duplet or octet states. So like I said earlier with helium and hydrogen. Now in this case now, helium it is complete already, hydrogen needs 1 electron. So if helium gives one of its electrons to this, it becomes an electrovalent or ionic combination. So in electrovalent or ionic combination, you have the donor, which is the electron giver. Now, donors are mostly elements in group 1, group 2 of the periodic table. Now, in previous classes where I talked about periodicity, I discussed families of elements. These are the alkali and the alkaline earth metals. Now, what does this mean by being donor? It means that group 1 element and group 2 elements, they have 1 or 2 valence electrons. So in their configuration, 1, 2, 1. And this is lithium. Lithium is a group 1 element. It has 1 electron in its outermost shell. So for it to obtain the duplet or octet state, it has to give out this electron to an atom which needs that electron. Now, by giving out this electron to the other atom, it becomes an electrovalent or ionic combination. So you have a donor which gives out electrons, and you have an acceptor. Acceptors are mostly in group 6, group 7 of the periodic table. So this group of the periodic table, they have 6 valence electrons. 6 valence electrons in the outermost shell, or 7 valence electrons. So to attain the octet state, they need just 1 electron. Just 1 electron. Now they need just 1 more electron here to attain its octet state. So this 1 more electron comes from the donor down here and gives it to this to form an electrovalent or ionic bond. So in this type of bond, you have the formation of ions, because a donor becomes a cation and the acceptor becomes an anion. So these strong charges, the attraction or the repulsion of these 2 charges is what brings out about the electrovalent and ionic bonding, which is very strong, which is a very strong force of attraction. Now, since the character of an element is unchanged by the chemical combination, since it is determined by the atomic number and not electrons. So in electrovalent bonding, this has 12 electrons, 12 protons, atomic number. This also has 13 proton, an atomic number of 13. So by giving out electrons, it doesn't affect its proton number. The proton number is the atomic number of the atom. Now A having 12 proton and having 12 electrons. Now to form bonds, now if it loses 2 electrons to become 10, the proton number is still the same because it is the property of the element. So it is in the nucleus. The nucleus is now in charge of losing electrons. So if an atom loses or gains electron, it doesn't affect the proton number. It only manipulates the electron number. So that's what this is trying to. It says the character of an element is unchanged by the chemical combination, since it is determined by the atomic number and not electrons. So the character of various elements, according to the periodic table, says periodicity. The periodic law states that the characteristics of elements is a periodic function of the atomic number. The atomic number is the proton number, not the electron number. So in electrovalent or ionic bonds now, we have great electrostatic force. Now because of the production of anions and cations, which are unlike charges, there is great repulsive force between these elements, leading to strong electrostatic forces of attraction because of the opposite charge particles of the elements. So in ionic bonds, you also have solids. Because of these strong forces, they tend to form solids mostly at room temperature, and they mostly have 3D crystal lattices. They have high melting and boiling points. Now, in order to break this strong electrostatic force, you need high amount of energy. which as a result brings about high melting points, high boiling points. They are mostly soluble in water because water is a polar solvent, while they are insoluble in polar solvent. Now, because of they readily form in anions, so on reaction with water ions, it easily comes into the bond to break this bond. So they react readily with polar solvents, water example, and they are electrical conductors. Hence, the liquids which conduct electricity are known as electrolytes. Now, electrovalent compounds are very good conductors of electricity, in the sense that by their combination you have charges are being formed, and we know charges are carriers of electrical current. So forms of electrovalent compounds in solutions are known as electrolytes. So an electrovalent compound which is a liquid is known as an electrolyte, because an electrolyte is a liquid which can conduct electricity, and it's only an electrovalent compound that conducts electricity. So in this case, the liquids are referred to as electrolytes. Now we'll be looking at very quick examples of electrovalent combinations, and the very typical example is what we see in sodium and chlorine. Now sodium has an atomic number of 11, chlorine has an atomic number of 17, and the electronic configuration of sodium is 2, 8, 1. The electronic configuration of chlorine is 2, 8, 7. Now what this means is that this is the duplet structure complete, octet structure complete. Now this is an incomplete structure. This is the duplet complete, octet complete, an incomplete structure. Now for sodium to attain its stable structure, it has to lose this electron in order to have a stable electronic configuration. For chlorine to be complete, it has to gain one more electron in order to attain a stable configuration. So in this case now, sodium atom transfers an electron to chlorine atom in order to attain a stable configuration. So in this case, sodium atom loses an electron to become a cation, and chlorine gains an electron to become an anion. So the combination of these two elements gives us sodium chloride, which is known as our table salts. So this is a typical form of electrovalent combination. So now we move to ordinary covalent combination, which is another example of electronic combination. Now, ordinary covalent combinations, there is no transfer of electrons between the atoms. Instead, there is a sharing of a pair of electrons between the two reacting atoms, so that both can attain the stable octet structure. Now, conversely to ionic or electrovalent bonding, in electrovalent bonding you have transfer of electrons from the donor to the acceptor, but in ordinary covalent bonding now you don't have transfer, instead sharing between two atoms. Now in electrovalent bond, you transfer your electron, you lose it completely, you are not concerned about it any longer, like what you see in sodium and chlorine. But in ordinary covalent bond, you don't transfer your electrons, instead both atoms share the electrons. So this is a different form of chemical combination compared to the electrovalent bond. So in the electrovalent bond, we have ions being formed due to losing and gaining of electrons. But since in ordinary covalent bonding, we don't have transfer of electrons, instead they share these electrons together. So in this case, we have the formation of molecules in ordinary covalent bond, because these electrons are in orbits around these two atoms which are sharing it. So in that case, you have formation of molecules. So now we'll be looking at lone pair and shared pairs, single, double, triple covalent bonds. Now since we said this combination deals with sharing electrons, now there are certain amount of electrons in the orbital that will be shared, while some will not be shared. So we'll be looking at that in an example. And you also have a single bond, a double bond, a triple bond. Now what this simply means is, now you have this. Now because we say there is no transfer of electrons, instead there is a sharing of electrons. In that case, what do we mean? So instead of this to move from A to B, there is no move transfer of electrons. Instead, they are sharing of electrons. So because they are sharing electrons, you have a connection between them. So this connection gives us this, which is known as the single bond. That is a single bond. Now this shared 2 electrons. Now, in a case where you have 4 electrons now being shared by the 2 atoms, A and B, A donated 2 electrons, B donated 2, so both of them share the 2 together to form 4. So in that case, you have a connection like this. This gives us the double bond. Also, you have when they donate 3 electron pairs now. A gives 3 electron pairs, and they share them together. They don't transfer them to each other. So you have 3. So in this case now, you have the single bond, you have the double bond, and you have the triple bond. So a single bond involves the sharing of 2 electrons. Double bond involves the sharing of 4 electrons. Triple bond involves the sharing of 3 electrons. So what this means is, in single bond you have 1 electron pair, double bond 2 electron pairs, and triple bond you have 3 electron pairs. This is what covalent bonding talks about, ordinary covalent bonding. So we'll be looking at lone pairs now and shared pairs in a typical example. Now an example of a covalent bonding is what we see in hydrogen gas. Hydrogen gas, which is H2. Now one atom of hydrogen and another atom of hydrogen comes together. The first atom of hydrogen has 1 atomic number. The electronic configuration is 1. It is 1. So it is not achieving the octet state or the duplet state 2 or 8. It is not achieving it. So in order to achieve this state, you need to have transfer of electrons or donation of electrons. Now, if hydrogen transfers 1 electron to this one, which is electrovalent bonding, this will be left to 0, which is not possible. So in this case now, they don't transfer them. Instead, they share the electrons together. So you have, now by sharing these 2 electrons together, you have so this is the configuration, just 1 electron, 1 electron. Now because it can't transfer this, electrovalent bonding is not possible in this case. So they share the electrons between the 2 atoms. So this gives us this. So the electronic configuration now of hydrogen molecule is 2, which is a stable duplet state. Simple covalent bonding. Another example is what we see in methane. Now methane, you have 1 carbon atom here, you have 4 hydrogen atoms here. So that is carbon plus hydrogen, 4 of hydrogen. The electronic configuration of carbon is 2, 4. The electronic configuration of hydrogen is 1. So in this case now, carbon needs to obtain the octet state. It has the duplet state. It needs to obtain the octet state. Now for it to obtain this octet state, it needs how many more electrons? It needs 4, because 4 plus 4 is 8. 8 is the octet state. It has the duplets already. Now hydrogen now has 1. For hydrogen to attain its own stable state also, it needs 1 electron to form the duplet state 2. So a transfer of electron cannot be possible here. Hydrogen can't give this 1 It can't just transfer 1 and become 0, not possible. So what happens here? They share the electrons now. So you have carbon now. This is carbon. 1, 2. So the duplets. Then that's 4 outside. 1, 2, 3, 4. And this is carbon. Now carbon needs 4 more electrons to obtain its stable octet structure. Now, and hydrogen has 1. So you have 4 atoms of hydrogen. So in this case now, you have the first atom of hydrogen coming here. You have another atom of hydrogen, another atom of hydrogen, another atom of hydrogen. So what simply happened here? This is carbon at the center. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now on sharing electrons with hydrogen, 4 hydrogen, hydrogen had 1 initially. So it came to share its 1 with each of these to form the octet structure. So in this case now you have hydrogen has 2 electrons, complete. The hydrogen here has 2 electrons, complete. Hydrogen has 2 electrons, complete. This also has 2, complete. Now carbon now has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. So what just happened here is that since carbon needed 4 electrons, so 4 atoms of hydrogen came in. So the first atom of hydrogen came, you are left with 3. The second atom came, you are left with 2. The next one came, you are left with 1. And the last one came in, you are left with 0. So in that case now, 4 hydrogen atoms came in now to share their single electrons with this to form a covalent bond. It did not transfer its electron to become an ion. Instead, it simply shared the electron. So further examples of covalent bond is what we see in chlorine, is what we see in water, and most organic molecules. So in covalent bonds now, they are mostly gases or volatile liquids. They are electrically neutral in the sense that you don't have the formation of anions. Instead, you have formation of molecules. So they are often gases and volatile liquids. They are electrically neutral compounds. They have low melting and boiling points due to their weak intermolecular forces. Now, because they don't have ions which have high electrostatic forces of repulsion or attraction, they have weak molecular forces. So this brings about low melting points and low melting and boiling points compared to the high melting and boiling point of ionic compounds. And they are bad conductors of electricity. Simple, they don't have charges, so they are bad conductors of electricity. So they are liquids and non-electrolytes. If you remember, for ionic bonding, their liquids are known as electrolytes because they can conduct electricity. So in this case, they are non-electrolytes. Now, covalent compounds also, they are soluble in non-polar solvents. Now, for ionic compounds, they are soluble in polar solvents, while for ordinary covalent bond, they are soluble in non-polar solvents. Soluble in non-polar solvents. So this is so that will be that on covalent bonding. So if I move to the next type of bond, you need to understand well that ionic bonding, you have covalent bonding. Ionic bonding deals with electron transfer from a donor to an acceptor. But in covalent bonding, you have the sharing of electrons. They share these electrons, they don't transfer it to themselves, they share it between themselves. So a third main type of bond also in elements, between elements, is what referred to as the coordinate covalent combination. Now the first which I talked about was ionic combination. Then I talked about ordinary covalent combination. Now we'll be talking about coordinate covalent combination. Now in coordinate covalent combination, it is also known as dative covalent combination. So we have ionic, we have ordinary covalent, and we have dative covalent or dative or coordinate covalent. So you have ionic bonding, ordinary covalent bonding, dative or coordinate covalent bonding. Now in coordinate covalent bonding, also known as dative. Now unlike the ordinary covalent bond, in which the shared pair is contributed equally by the two participating atoms. Now if you remember that in ordinary covalent, the two participating atoms A and B, they both provide the electrons to be shared between them. But in the case of coordinate covalent bonding, the pair in the coordinate covalent bond is donated by only one participant. So for this type of bonding now you have A and B. Now the electron that they are going to be sharing will be provided only by B. Only provided by B to be shared among them. So in this case now, A doesn't provide any electron. Instead, this provides it and share it with A. It doesn't transfer it to A. So the pair in the coordinate covalent bond is donated by only one participant. So this simple analysis is what will help us in differentiating this type of bonds between elements. For ionic, you transfer atoms to gain your octet state. For ordinary covalent, you share atoms, you share electrons between two atoms. Two atoms provides these electrons to be shared. But for coordinate covalent, the shared pair of electrons is provided by one atom. So ionic involves two atoms, one donor, one receiver. Covalent involves two atoms, both sharing electrons that they donated. Ordinary coordinate covalent involves sharing of electrons between two atoms, but with one provider. Simple. So an example is what we are going to be seeing in ammonium ion. Now in ammonium ion, you have the combination of ammonia and hydrogen. So for ammonia now, you have ammonia NH3. This is ammonia. Now, in ammonia, you have a covalent bond. You have ordinary covalent bonding here, in the sense that now nitrogen has a configuration of 2, 5. That's 7 electrons. Hydrogen has a configuration of just 1. So in this case now, hydrogen needs 1 electron to attain the duplet state. Nitrogen needs 3 electrons to attain its octet state. So because hydrogen can transfer 1 to become 0, and this needs 3. So in this case now, 3 hydrogen atoms comes to rescue the nitrogen atom. So in this case now, you have 1, 2, 3. So they share this electron. So that is why you have this. This is the covalent bonding between them. Remember that this means 2 electrons are being shared. While when you have this, you have 2 electrons pair. That is 4 electrons are being shared. So in this case now, you have an ammonia gas, which is a covalent molecule. Now combines with hydrogen ion now. Now combining with hydrogen ion, it forms ammonium. It forms ammonium ion. Now recall that this has formed a bond to attain its state already. It is complete already. But on combination of ammonia gas with hydrochloric acid, which gives out positive hydrogen ion. Now combining with this, it forms this. Now this plus here signifies that it lost one electron. Now this is already balanced already. It is balanced. So for it to continue to undergo chemical combination by gaining this H plus, it has to lose one of its electrons to become an ion. So this is a dative covalent bonding. Now because the electron pair which is being shared now is provided by just the hydrogen ions now, and the hydrogen ions are the provider of the shared electrons. Nitrogen did not contribute any. So this is a dative covalent bonding. So examples of the coordinate covalent combination is what we see in ammonium ion, oxonium ion also, which is a combination of also hydrogen ion plus water to give us hydroxonium ion. Hydrogen ion, and this is water. Water is a covalent bonding. It's covalent bonding between hydrogen and water. Now hydrogen and oxygen both donate 2 pairs of electrons to form the covalent bond. Now in addition, on reaction with this, you form H3O, which is oxonium ion. This is already in its complete state, complete octet structure. Now introduction of this has to lose one of its electrons to gain H plus. So that gives us H30 plus oxonium ion. So we also have compounds similar to covalent bond molecules but less volatile. So for coordinate covalent combination, their compounds are similar to covalent bond molecules but they are less volatile. So other binding forces in chemistry, we have metallic bonding. So for metallic bonding, you are talking about forces of attraction which would hold metal atoms together in crystal lattice. Now we all know metals have 1 or 2 valence electrons. Metals, we're talking about metals now. Now the forces of attraction which would hold metal atoms together in crystal lattice is what referred to as metallic bond. Now you have various atoms of a metal coming together, and you have electrons, mobile electrons in orbit about this complex structure now. So for metallic bonding, you have various atoms of metals coming together to form bonding. Now these are the atoms. Now metals have valence electrons, lots of valence electrons. So this minus depicts the electrons. Now this orbit of the valence electrons about the nucleus of this combination of metals is what referred to as metallic bonding. So metallic bonding occurs in metals. And also we have van der Waals forces. Now van der Waals forces are weak attractive forces existing between discrete molecules. And these are weak forces when compared to ionic bond or covalent bonding. And they are important in liquefying gases in the formulation of molecular lattices. So van der Waals forces are just weak forces of attraction which occur in molecules also. So lastly here we have hydrogen bond. And this is an intermolecular force which arises when hydrogen is covalently linked to elements like nitrogen, oxygen and fluorine. Now in hydrogen bonding is a bond between hydrogen and strongly electronegative elements. Now when hydrogen is bonded, it can be in covalent bond with different atoms. Now let's say you have HF, it's a covalent bond. Now you have a covalent bond of hydrogen fluorine. Now the weak intermolecular forces between hydrogen and this highly electronegative metal brings about the hydrogen bonding. So for hydrogen fluoride now, which is you have hydrogen, you have a weak force to fluorine now, and the hydrogen bonding. the covalent bond. You have a weak force to fluorine, you have the covalent bonding. So this occurs throughout the lattice of this compound. So an hydrogen bond occurs between hydrogen and strongly electronegative elements. So these three forces, which are weak forces, they are weaker when compared to your covalent bond, your electrovalent bond. So these are just weaker forces which also exist between molecules. So quickly now, we'll be looking at some examples here. Now I have an exercise here. We have various compounds now. We are asked to label the following as ionic or covalent bonds. Now this, we are just applying the knowledge now which we have studied about bonding. Now I want to name these compounds according to the bonds they have between them. So first off, I'll be taking CCl4, which is carbon chloride. And this is an organic molecule. Now you have calcium and you have chloride. Now first, the configuration now, the atomic configuration for calcium is carbon, this is not calcium, sorry, this is carbon chloride. So carbon is 2,4, and for chlorine you have 2,8,7. And this is, so carbon needs 4 electrons to complete its octet structure. Chlorine needs just 1 electron. Now this is carbon, and this is chlorine. 1, 2, 3, 4, 5, 6, 7. This is 8. This is 2 8s, and this is 7. So I need 1 here, while this needs 4. Needs 4 to complete its octet structure. This needs just 1 to complete its own octet structure. So the combination between carbon and chlorine now is a covalent bond. Why? Because 4 atoms of chlorine will come to fill these places now. Now this needs just 1, this needs 4. So first atom of chlorine comes to share here, the second comes to share here, the third comes to share here, and the fourth comes to share here. So this gives us CCl4. In other words, you have a structure like this. So what this simply means, as you can see, carbon needs 4 electrons, chlorine needs 1 electron. So chlorine shares with the carbon electron. And this has 7, this has, carbon has 4. On sharing this with this now, chlorine becomes 8. Now carbon gains 1 here, gains 1 here, gains 1 here, and gains 1 here. So 4 plus 4 gives us 8. So it's a very simple analogy here now. So this is a covalent bonding. It is not ionic because it did not give this to become 1, 2, 3, 4, 5, 6. Instead, it's shared. So 4 atoms of chlorine came in to share with the carbon atom. Okay, so now I'm looking at potassium and bromine now. You have potassium and you have bromine. And the electronic configuration of potassium is 2, 8, 8, 1. This is 2, 8, 18, and 7. It's a very large element. So for the K shell, L shell, M shell, you have this. Also for the K shell, the L shell, the M shell, you also have this for potassium. So you can see here now that for potassium it needs just 1 electron to attain its octet state. And for bromine also needs 1 to attain its octet state. So what this means is that this can lose this electron to have a complete state, while this needs just 1 electron to become 8 to attain its octet state. Now they don't need to share electrons to attain octet state, because as it's been seen now, you have the configuration now. This is 2, 8, 8, and 1, which is chlorine. Now same for the bromine. This is its outermost. It needs just 1 here now. So in this case now you have 2, 8, 18 inside. Don't forget 2, 8, 18. This is just the outermost shell 7. Now because covalency cannot occur here, because if they share this electron, they share it, this have complete structure, but this we still need 7. So instead, chlorine loses this. It loses this electron, while bromine gains 1 electron to give us KBr. So this is an ionic combination. So the last example I'll be looking at here, I'll implore us to try this, try out this, try out this, try out this, try out this, and this will give us a covalent bond. This will give us, okay, let me solve this now. This, we have hydrogen configuration of 1, configuration 287. Now to attain octet state, this needs 1, because it can't lose 1 to become 0, while this needs 1. They both need 1 each to attain duplets, to attain octets. So what simply happens here, you have 1, 1, 2, 3, 4, 5, 6, 7. So they share this electron between them to form HCl, which is covalent. So you have something like this. One, 2, 3, 4, 7. 1, 2, 3, 4, 5, 6, 7. 7. So this is the shared electron pair between them. So this gives us a covalent bonding. This gives us ionic bonding. And this gives us ionic bonding. This gives us covalent. This is also covalent. This is also covalent. This is covalent. And so on. So I'll employ us to try out various compounds to ascertain the type of bonding between them. Thanks.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.